And we'll go straight into the questions. We have quite a few coming in from the audience, also many with numerous likes. So let me just plunge right in. And here's the first question. If trucks will use liquid hydrogen compressed cryo and 70 bar on the German roads, are you planning to build combined stations for all of these trucks?
Well, that's actually nothing we considered in our study. It's rather unlikely that you will see all three fuel types in parallel. So I guess the industry needs to agree on one or two of those fuels, at least for the long distance trucking. But of course, if the choice would be, okay, we do all three fuels at the same time for different truck sectors or different manufacturers, that would also be feasible. And actually, you would have quite large synergy effects between those fuels if you integrate them in one refueling station.
Thank you very much. And next question, did you consider the transport and use of ammonia as a hydrogen carrier?
We did not look at this supply chain in this study, so I cannot say anything from this study, but within our company we have done multiple studies where we also included other hydrogen carriers, including ammonia, and our finding is that ammonia might be a feasible hydrogen vector for some application, but it's most likely not feasible for the vehicle sector because you just add up too many conversions. If you go from hydrogen production, ammonia shipping, then you need cracking of ammonia to hydrogen, and then you again need to do something with the hydrogen to get fuel out of it, either compression or liquefaction. That's just not cost and energy efficient.
Thank you very much. Next question. What is the prognosis for the German industry's ability to meet the projected fuel demand for 2035 combined with demand for passenger vehicles and move current hydrogen production away from refining to meet demand?
Yeah, well, that's a big challenge, actually, to ramp up the international production capabilities for electrolyzers. But that's nothing we had a close look at in our study. But it's a challenging task, of course, but it might be feasible.
Then here comes the next one. What is the estimated average mileage and consumption per truck and year in your base calculation?
Yes, you can actually look that up on one of the slides, which will be available after this presentation. For new sold vehicles, we usually see very high mileage of about 120,000 kilometers per year. If then the trucks get older, they usually get sold and resold. And the older the trucks are, the lower the number of kilometers you drive, usually. But for new sold vehicles, and in this application and in those classes, it's about 120,000. And the fuel consumption is between about 7 and 7.5 kilograms of hydrogen per 100 kilometers, which is about 60 miles.
Thank you very much. Next question. On slide 10, it looks like the 70 bar hydrogen refueling stations can only be supplied by 50 bar trailers and not by liquid hydrogen distribution from liquefaction. Why are you not planning to provide liquid hydrogen to the 70 bar stations from this source? It could be beneficial in case of long distance between the pipeline and the hydrogen refueling station.
Yes, that's absolutely correct. In case we have long distances between the pipeline and the refueling stations, it might be more feasible to have liquefaction just for the transport, and that's what the question is about. Does it make sense to only liquefy hydrogen for the transport between the pipeline and the refueling station? We have not considered this option actually in our study, but I would assume that with the electricity price you pay in Germany for industry, it might not be cost competitive to do this extra liquefaction, but we have not looked at it.
Thank you very much. I come to the next question. Around what time frame would you anticipate beginning imports into Germany?
Well, the European strategy clearly indicates that there might be hydrogen imports starting in 2030. However, the challenge would be to have the technology available by then to enable that import. That's true for LH2 imports. As you might know, there are currently no large-scale liquefiers, at least not in that scale that we would require 3-digit tons per day. You don't have those LH2 carriers available yet, and all the infrastructure. There's just the demonstration project running between Australia and Japan right now. And for the pipeline case, here the most technologies are actually available, and for Germany and Europe, it's planned to mainly use repurposed natural gas pipeline for hydrogen transport. But here you might have the challenge until 2030 to get sufficient capacities freed from natural gas and transferred to hydrogen use. And then you also need to fill the gaps with new pipeline segments in some cases. So it's a challenging task, but around about 2030, 2035, we might see hydrogen imports.
Thank you very much. Next question. Herr Zerhusen, could you elaborate further on cryocompressed hydrogen, CCH2?
I could actually, but I will not, because that's the content of the following presentations.
Thank you very much. Are you planning to replace the existing fueling stations or establish new ones for hydrogen?
I think both could be an option, but most likely we will see rather putting hydrogen where the current conventional diesel stations are, at least for the highway system, because there's a good reason for the location today. And that's, you also have different infrastructure, you have restaurants and toilets, you start seeing the electricity chargers being located there, though you might as well just place the hydrogen station there as well. And the same might be true for truck depots. If you have a private diesel station there today, those operators might also think about their own refueling infrastructure in the future. So it's most likely will be the same sites and location for trucks. It's a little bit different for light-duty vehicle, but that's not the topic today.
Thank you very much. And next question reads, what assumptions went into okay, it just disappeared from my, here we go, it's back. What assumptions went into the liquefaction? E.g., how many tons per day are needed at the source? Is the technology actually available? And gaseous hydrogen tube trailer. For example, did you consider the recent change in ADR that allows to transport 1.5 tons of hydrogen per truckload? And what compressor developments were anticipated?
Okay, that's three questions at once. Let's start with the liquefaction plant. Here we have assumed, and that's what's required, very large-scale liquefiers, so 3-digit tons per day capacity, and that enables a significant improvement of the electricity consumption or the efficiency, so to say. And of course also some cost scaling effects. But this technology has not been built and tested yet. We see 30 tons per day stations. I think there have been 50 tons per day stations as well, but we've not seen 100, 200, or 300 tons per day stations yet. It's not not tested. Yes, we have actually considered the changes in ADR for the 50 megapascal road trailer transport. Those 1.5 tons of hydrogen are the gross transport capacity. Usually you do not empty the trailer at the refueling station all the way, because then you would actually require quite expensive compressors at the refueling station. So there's always some pressure going back to the hydrogen source. So the actual net transport capacity of those new ADR trailers is a little less, especially in Europe, as we have different limitations in length with the trailers. So we assume that the net transport capacity is around about 1.2 or 1.3 tons of hydrogen, but of course depending always on the pressure in the returning trailer. The third question was regarding the improvement of the compressors. Yes, here we have assumed some improvements in terms of cost reduction, also in terms of compression efficiency, which is quite relevant, and also in lifetime. Here, our data was based on industry consumptions, but we also looked at targets, for example, formulated internationally by the DOE. And we have also assumed improvements in terms of compression concept at the refueling station. So we have assumed that the gaseous hydrogen trailer, which was the second question actually, is integrated in the refueling station. So we enable direct refueling, at least in parts, from this trailer vessel to the receiving vessel at the vehicle. So we do not need compression for a certain amount of hydrogen. And then, of course, the other hydrogen needs to be compressed because we need up to 95 megapascal for refueling. So we have assumed a new and improved concept for the refueling station. However, always based on the current state of the art in terms of refueling protocol, which is pressure differential refueling. We have not assumed booster concept refueling, which might allow even lower costs for the refueling station for 70 megapascal in the future, but that was not considered.
Thank you very much. Let's see if we can squeeze in just a couple more because they're still coming in. Did you consider LOHC as a transportation vector in comparison to liquid hydrogen?
Yes, we did. We did look at LOHC as well. We found that if you want to have liquid, cryocompressed, or 70 megapascal hydrogen fuel, LOHC, and here we used, LOHC is a group of components. We used DBT as component. We found that that's not attractive in terms of economics, and that has one simple reason. First of all, you need a lot of energy to dehydrate the LOHC, around about 30% of the energy in the hydrogen. And of course, if you have some energy deficit in a country, so you import hydrogen, for example, to Germany, that's an indication there's an energy deficit. So you usually have rather high energy prices, you have to assume here. So that brings up the cost, and then the resulting hydrogen from the dehydrogenation unit, that's a low pressure hydrogen. Here you need additional investments at the refueling station for intermediate storage at low pressure, and then additional capex for the lower suction pressure of the refueling station. So we have looked at it, but it seems not cost competitive.
Thank you very much. And we have one more I'd like to do, if we can get up on the screen. Please explain the durability of cryocompressed related to the life of the truck, 1 million kilometers, and safety. Okay. What happens? Sorry, there is a little bit more.
Don't worry.
Okay.
This question would be answered by the colleagues from Cryomotive anyway.
Okay, excellent.
So that's not my topic. Thank you.
Excellent. Then we're right on time. And I'll just say thank you very much, Jan Zerhusen, both for your insights that you shared with us and for being available to take so many questions from a clearly very interested audience.
Thank you very much.